This video is an introduction to chemical reactions and chemical reaction equations, and a brief introduction to stoichiometry. So we're going to start by just talking about reactions in general. Some of these things may be things you already know. So what you see here on the top are models that show you a picture of this reaction, and the bottom is a chemical reaction equation. So in a chemical reaction equation, what's on the left of the arrow, those are reactants, which react together to form products. The arrow is called a reaction arrow, and on the other side are the products. Now you're always going to have one or more reactants, you're always going to have one or more products. And other pieces of these equations, sometimes you have things that are required for the reaction but are not reactants or products. And so, for example, heat is something sometimes you need for a reaction to proceed, or you might need high pressure, or you might need a catalyst. We're going to talk more about catalysts next semester, but catalysts increase the rate of reactions. And so any of those required things that are not reactants or products would go on the arrow. You would directly write them on the arrow. So sometimes you see things written on the arrow. Now, reactants and products are also collectively sometimes called, or more generally called, reaction components. And so hydrogen, oxygen, and water are all considered reaction components for this reaction. That's just sort of a general term for anything in the reaction that's a reactant or a product. Now, states of matter are typically included in parentheses after each component. And so sometimes you see them subscripted, but they're usually in parentheses, whether they're subscripted or just regular. Sometimes they're italicized like they are here. The formatting varies, but usually there is an abbreviation there that indicates the state of matter. This table would help you know which state of matter it is. Most of us are familiar with solids, which would be S, liquids, which is L, gases, which are abbreviated G in the reaction equation. Also, a possibility that's very common is to see AQ. AQ stands for aqueous. When you have a reaction component that is dissolved in water, it's listed as aqueous. Very occasionally, you will see reaction components that are dissolved in some sort of solvent that is not water, and if that is true, instead of using AQ, it will use the abbreviation for solution, which is SOLN. That's a pretty rare occurrence, but you might see it. In this particular reaction, we have two gases reacting to form a liquid. Now let's move on and talk about the here. So the numbers in front of reaction components are stoichiometric coefficients. So for example, there's a 2 in front of the hydrogen gas, and there's a 2 in front of the water molecule that's the product. There's nothing written in front of the oxygen. The number 1 is always understood, and it is not typically written in a reaction. So a way of interpreting this reaction would be to say 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to form 2 molecules of liquid water. So that's one interpretation of this. Another way to think about this reaction is if we had a whole bunch of hydrogen and oxygen and water. Let's say we have a lab-sized sample, which we've talked about earlier in the semester, but we'll continue to talk about more and more. Another way of describing this reaction, so let's say instead of, we don't want to make water. Water's our product here, but let's say we don't want, let's say we're Cookie Monster and we want some cookies. So Cookie Monster wants to make a whole bunch of cookies. And I want you to think about reaction equations sort of the same way you would think about making anything like cookies. You have ingredients that would be the reactants, and the cookies are our products. Some reactants. We're going to take some flour and some butter and some chocolate chips and some sugar. We're going to put those together and we're going to make some cookies. But we're not going to mix them together in some random proportion that we don't know how much to add. We're not going to just throw in things willy-nilly because we know that the cookies won't turn out right. The only way that the cookies will turn out right is if we use a recipe. So we're definitely going to use a recipe. So the way you need to think about a chemical reaction equation is that it's a recipe that absolutely has to be followed. Okay, so here we want to make water. instead of making cookies. And we're going to use the recipe. My recipe for water says I need 2 molecules of hydrogen and 1 molecule of oxygen. And I am going to stick to that recipe, right? Now we're going to practice writing some chemical reaction equations. We're going to do this next. And then we're going to talk in subsequent videos about how we're going to use the reaction equations to do some chemistry math. So here we're going to practice writing chemical equations. It's really important that you know nomenclature for this. It's going to be hard to write any of these reactions without knowing the formulas of the compounds that are going to be given to you in word format. So we'll start with A. An aqueous solution of ammonium perchlorate reacts with solid aluminum to form solid aluminum oxide, nitrogen gas, chlorine gas, and water. So we're going to start with the first reactant, ammonium perchlorate. And we know it's aqueous, that's given in the problem. Ammonium is NH4 with a +1 charge. Perchlorate is ClO4 with a -1 charge. So those go together 1 to 1. And we need to put AQ after it for aqueous. Solid aluminum means we just need Al with an S. There are a few elements that you need to know that are diatomic or polyatomic. We will talk about those in class. And there's a previous video that describes those. If you go back in the videos to when we just went over the periodic table and the different forms, I think it was probably molecules, compounds, and elements video. Some elements exist in a diatomic form, and those include hydrogen, oxygen, nitrogen, and all of the halogens, right? So group 7A. A few of them also form unusual allotropes, like there's an allotrope of sulfur called S8, and there's an allotrope of phosphorus called P4. Other allotropes like those, I will tell you what they are. And if you don't know, just write a single atom, like you see here, a monatomic aluminum. If it's not diatomic, then I would expect you to just write it monatomic like this. You do need the S in parentheses. It does tell you solid aluminum there. And then when you see the word to form means that the arrow goes there. Okay, so then the arrow, solid aluminum oxide. So aluminum oxide is just binary. It's a binary salt. And so we have binary means it has 2 elements. Salt means it's an ionic compound. And so aluminum is in group 3A, which means it has a +3 charge. Oxide is 2 columns to the left of the noble gases, which means it has a -2 charge. So aluminum oxide goes together with 2 aluminums and 3 oxides to make an overall 0 charge. Okay, if you're still having problems with that, let me know. We can work on writing those formulas. But that's the hardest part of this, is writing the formulas. And then we also form nitrogen gas. Nitrogen is one of the diatomic elements, and so you have to write N2 with a gas. Chlorine is also diatomic because it's one of the halogens, and you do need to know that. So that's Cl2 with a G in parentheses. And then water, you assume is liquid water, so plus H2O liquid. Now I'm going to warn you that this particular reaction equation is unusually difficult to balance. Most of the reaction equations you get will be relatively simple. This one is quite difficult compared to others, and I wanted to give you one that was hard just to show you how hard it can be. If I give you one that's this hard, it would be on a homework where you could use your book or have more time to think about it. On quizzes, they will generally be easier to solve, like B or C. All right. So when you're trying to balance this, one thing I want you to really think about is whenever you have an element in its elemental form, so you see aluminum there in its elemental form, and you see nitrogen, N2, and Cl2, and they're in their elemental form, think about those as being sort of a helpful to you in the end, because you can manipulate those without influencing anything else. So what you'll see is that, when you put a coefficient in front of a compound, then it influences everything in that compound, and sometimes that makes things more complicated. So what I'm going to do to simplify things here is, because I have one nitrogen on the left, you see NH4Cl O4, there's one nitrogen there, and there's one chlorine there. And I'm kind of, I don't like, I could put a 2 in front of that molecule, but then there's going to end up being 8 hydrogens, and then I need a 4 in front of the water. And then there's going to be 8 oxygens, and I've got a weird number of oxygens on the right. We've got 3 and 0. So in order to initially go ahead and balance nitrogen and chlorine right off the bat, is I'm just going to put a 1/2 in front of the N2 and the Cl2. And that will immediately balance those two in my formula, in my equation right now, because you see there's 1 nitrogen on the left, there's 2 on the right, but I put a 1/2 in front of the N2, and that gives me 1. Now at the end, I'm not going to have halves or fractions, and so I'm going to multiply through at the end. But for now, nitrogen and chlorine are both balanced in this reaction. And we'll deal with the fractions at the end. Okay, so I've started off with just balancing nitrogen and chlorine just to make my life easier. I can ignore those for now. Now we're going to move on, and we're going to look at the next element that we're going to do. And let me hit play again. There we go. So here I have, let me back it up a little bit just to make it, there we go. Okay, so here, the next thing I balanced was hydrogen. So you can see that there's 4 hydrogens in ammonium perchlorate. That's the entire left side only has 4 hydrogens. The right side, the only compound that has hydrogen in it is water. So I'm going to put a 2 in front of the water, and that gives me 4 hydrogens. So at this point, I have balanced nitrogen, hydrogen, and chlorine. And then next, we're going to look at oxygen. And oxygen is a little complicated because we've got 4 on the left here, and then we've got 3 and 2 here. So there's 5 on the right. And that makes it a little bit hard to figure out. Okay, so what I want you to see is that there's 4 on the left, and that's definitely true. There's 2 contributed by water. So if I could just get 2 from this molecule, then I can balance the aluminum all by itself. So how do I get 2 oxygens out of a molecule that contributes 3? Right? And so think about this mathematically. If I have 2/3 of this molecule, then that's going to give me 2 times 3 is 6, divided by 3 is 2. That would, if 2/3 of this molecule will provide just 2 oxygen atoms. And I know it doesn't, it's hard to wrap your brain around what that means conceptually, but we're going to get rid of the fractions at the end. Okay, and we can do that mathematically. So think about it math-wise. If you have 3 oxygens being contributed, 2/3 of that will give you 2. Okay, so now with a 2/3 here and a 1/2 and a 1/2 and a 2, everything except aluminum is now balanced, because nitrogen, there's 1 here and there's 1 here. Hydrogen, there's 4, and on the right there's 4. Chlorine, there's 1, and 1/2 Cl2 gives me 1. Oxygen, there's 4 on the left, and there's 2 from water and 2 from aluminum oxide, so that gives me 4. So the only thing left to balance is aluminum, and here I have 2 times 2 is 4 divided by 3. Now I can just write 4/3 here, and that will balance the aluminum. But I think what I'm going to start with is just getting rid of all of these fractions. Okay, so if I multiply through and get rid of the fractions, that means I have to multiply everything through by 6, which is going to give me 6 ammonium perchlorates, 4 aluminum oxides, 3 nitrogens, 3 chlorines, and 12 waters. And then I have 8 aluminums at the end, and I'm going to add that in last. And so because this is just an elemental form, I can do this at the very end. Okay. Now I could have easily, before I could have said I need 4/3 of an aluminum here, and then when I multiplied through by 6, then 4 times 6 is 24, divided by 3 is 8. I would have gotten the same number. But the way my brain works, I find it easier to solve this aluminum at the very end. So this one is really hard. I'm going to just say that out front. Okay, I don't want you to be terribly concerned about it, because if I give you one this challenging, it's definitely going to be like a homework. Okay, they're usually much easier than this. All right, now let's move on and do B. This is my final answer for A. I'm going to circle it just so we know what the final answer is. And you always should go through and make sure everything balances at the very end. Liquid propanol, I give you the formula for that. And remember to write the little L. I write L in cursive when I'm writing, just so that it's very clear that it's not a 1. If you were, you can use manuscript, that's fine. But most people write in cursive. Combustion is an idea that I wanted to tell you about. If we go back to that word, combusts in air. Liquid propanol combusts in air. Now this is a reaction that we would have done in class. Combustion always involves the combination. It's typically a hydrocarbon. Hydrocarbon means that it contains hydrogen and carbon. That's why it's called a hydrocarbon. If we take a hydrocarbon and we put it in this flask and we add in some oxygen, in the problem it said it combusts in air, which would work because the air contains oxygen. Then what's going to happen is, once this magic happens, we're going to get some sort of product. Now the way I usually think about combustion is, because it's hard for me to remember things, combustion is the same thing that happens in us, right? So this is you, and you had an apple as a snack earlier. The apple is the hydrocarbon, okay? The hydrocarbon is like fuel to us, right? So an apple contains some sugar. That's my hydrocarbon, and I'm going to put it in. That's my food. That's the hydrocarbon. The oxygen I breathe in from the air, right? We all need oxygen to live, so that helps me remember that oxygen goes into a combustion reaction. We need food to live, so the hydrocarbon's going in my mouth too. And then when you think about the products, right, what are the products of our own combustion, our own respiration, right? So from biology and from science class that you've taken since you were in elementary school, I know that you know that we inhale oxygen and we exhale carbon dioxide. So carbon dioxide is also a product of combustion. Now another thing I like to sort of think about is water is the other product of combustion. You can see that that's coming out of this combustion reaction here. But water is also a product of respiration, and so water comes out everywhere, right? You spit, you sweat, you gotta go pee. Water comes out everywhere, right? So water is always a product. Water. Now, so if we write those reactants and products that we know, this is all I'm going to tell you in a problem. I'm going to give you the formula for the hydrocarbon and the state of matter. So liquid propanol, here's the formula. Combusts in air, that's all the information you're given. So you have to know that oxygen is a reactant. You have to know that carbon dioxide and water are products. I would not care if you put liquid water or gaseous water here, but oxygen is definitely diatomic and it is definitely a gas. Carbon dioxide has this formula and it is definitely a gas. Now the last thing we need to do is we need to balance it. So if we count up the number of carbons on the left-hand side, we have 3. And then on the right-hand side, we just have carbon dioxide. So we need a 3 coefficient in front of the CO2. Then if we count up the number of hydrogens, we have 3, 4, 5, 6, 7, 8 hydrogens, which means I need a 4 in front of the water. Now we have oxygen to balance last. And so I want you to remember that there is an oxygen contributed from that propanol. If we add up the oxygens on the right-hand side, we have 3 times 2 is 6, plus 4 is 10. 10 oxygens on the right. There is 1 oxygen contributed from propanol, which means 9 of them have to come from O2. So that means we need 9 more to come from this molecule, which means I need a 9 halves. Okay. So at the end of the day, we're not going to leave that fraction in there. We're going to multiply everything through to get rid of all fractions, which means I need to multiply by 2 to get rid of the 9 halves. And so that's going to form 2 is the first coefficient, and 1 is the second coefficient, or 9 is the second coefficient. This one is going to become a 6, and the last one is going to become an 8. And that's going to be my final answer. Now, whenever you finish, when it says you have to write a balanced chemical reaction, It needs to have whole numbers, integers, not fractions, and it needs to have the lowest possible integer. Okay, so in other words, if you gave me an answer here that had 4 propanols and 18 oxygens and 12 carbon dioxides and 16 waters, that would not be worth full credit to me because that is not the lowest integer value possible. And if you included fractions, that would also not be for full credit. I expect you to use whole number integers, okay? And the lowest whole number integer possible. So try to remember that. Part C, solid aluminum nitrate decomposes to form molecular nitrogen, water, and a gas that reignites a glowing splint. So here we have solid ammonium nitrate. We're going to write ammonium, which is NH4 with a +1 charge. Nitrate is NO3 with a -1 charge. It's a solid, so ammonium and nitrate go together 1 to give a 0 overall charge compound. Decomposes. That word decomposes kind of implies that there's a single reactant, and that's where the arrow would be. We're going to form molecular nitrogen. That's another word for N2. That means nitrogen as a molecule. Nitrogen is a gas, so I expect you to know that. Water, you're going to write H2O liquid. And a gas that reignites a glowing splint. So this is one of the splint tests that you did in class, and I do want you to know the different splint tests and the different reactions or things that would happen and the indications of what gas. So a gas that reignites a glowing splint is definitely oxygen. But I want to make sure we remember the different splint tests. So let's see, there are 3 splint tests. Let's start with this one. We're going to insert a glow. This is a flaming splint. This is a flint that is on fire. There's an active flame there, and it pops. So if you insert a flaming splint into a test tube that contains a gas that causes it to make a loud pop, then that is the positive splint test for hydrogen gas. If we take our flaming splint again, see it's on fire, and we insert it into a test tube with a gas, and the gas causes the flame to extinguish and go away. So if we extinguish a flaming splint, that is a positive splint test for carbon dioxide gas. And then if we insert a glowing splint, and that's what this is supposed to show you, is that there's just a little bit of orange glow left on the splint. So I ignited it, it was flaming, and then I blew out the flame, and it was still glowing orange. So that's what we would call a glowing splint. The fire has been blown out, but it's still glowing a little bit. And we insert the glowing splint into the gas, and that causes it, once I do that, to reignite, like I'm showing here. That is a positive splint test for oxygen. So that means that we have reignited a glowing splint. That is a positive test for oxygen, so oxygen is my last product. Next, I'm going to balance this reaction equation. I have 2 nitrogens on the left, and I already have 2 nitrogens on the right, so I don't need a coefficient there. I have 4 hydrogens on the left, and I only have 2 on the right, so I need a coefficient of 2. Now the oxygen, there's 3 on the left, and there's 4 on the right, right? There's a 2 in front of this water, and then there's O2, which means that I really only need a 1/2 O2, which means I need to put in the 1/2, and then I'm going to multiply everything through by 2, which makes a 2 and a 2, and water will be a 4, and oxygen will go away and be a 1. And that's my final answer for part C.